Hi everybody, Professor Hyman, IBUS 620. I got some notes and some stuff to talk about regarding measurement of variation in data. Okay, you guys have a pretty good grip on stuff like the mean, the median, and the mode, stuff you've seen before, stuff that's very straightforward to calculate. Variation, slightly different. Some of it's easy, some of it's slightly less easy. Let's just talk about right now the question of n minus 1 in the standard deviation. And I'll clarify what I mean by n minus 1. It's in quotes in just a moment. Okay? So remember our notation. First thing is that x bar, which is x with a line over it, small x with a line over it, is the mean of the sample. And if you're typing at a keyboard and there's no character for x bar, which is extremely common, then you can write the word x bar or x hyphen bar, uppercase, lowercase, whatever you like on that one. Okay? And then n is the number of data points, and I is just an index or a counter. And it allows us to count from 1 to n iteratively. And let me explain that in the formula, which is where we're going next. But first, I'm going to just offer this clarification where the standard deviation notation is SD, standard deviation, or S. And this is more common. And we use S in the algebraic formulas to express the values that we're calculating. So S, small s for this one. So here's the formula for S. Standard deviation equals the square root of this entire thing, okay, which is the sum from I equals 1 to n of x sub I minus the mean quantity squared divided by n minus 1. Now let's deconstruct that briefly, okay? Start in the parentheses. Small x sub I is a data point. It could be the first, second, third, fourth, or nth data point. But you take a data point, you subtract x bar from it, you square it, you take the next data point, you subtract x bar from it, you square it, and you add them all together. Just keep doing that and adding them all together from 1 to n until you have the sum of the squared deviations from the mean. This is just the deviation from the mean, x sub I minus x bar. Take the deviation from the mean, square it, and then sum all those deviations from the mean from 1 to n for each data point. Divide the whole thing by n minus 1, and then take the square root. That's S. It's a measure of variation in your data. I want to note briefly that variance is S squared. It's another measure of variation, okay? Variance is just the square of S, which means you essentially get rid of this square root sign, get rid of the radical, and it's just calculated this way. However, we don't use the variance, or S squared, very much. It's used as an intermediate product sometimes in calculations, but we don't use it very much as something we say, and this is the variance, because it's not as useful because it's harder to interpret, okay? It's not as useful as S because interpreting S squared or the variance is harder, because if you take this square root away, what you have is units that are squared. Let's say you're taking the mean of people's income in dollars, okay? If you use S with the square root in it, at the end of the day you come out with units of dollars. But if you take this square root away, you're calculating the variation in dollars squared or square dollars, whatever those are. The point is that's not easy to understand. Maybe it's not even comprehensible. And so we take the square root, which puts the dollars squared back to dollars. Okay, so this is the standard deviation formula, and it's much better than the variance formula for talking about the nature of the data because you can interpret the units more coherently. Now, let's move onward, because this whole formula inspires the question, why n minus 1? In fact, why n minus 1? Well, n, instead of n minus 1 here, would make this formula into the actual mean of the deviations from the mean, and the mean of a mean is actually a pretty powerful statistic. It tends to be meaningful, to make a horrible pun. Okay, but we don't use n. We use n minus 1. Why? Okay, and the answer is up here, and it is the n minus 1 is more conservative. So when you have anything over n, you're calculating the best possible value, remembering that smaller s's are better. Smaller standard deviations means you have a more concrete and more accurate measure of the central tendency of the data, which is what you want, all right? But in science, you can't just calculate things because you want them to be a certain way. So to be conservative, we use n-1. And if you take, for any fraction, any expression, that's why I've got a squiggle up here, divided by n is always less than that same expression divided by n-1. It's the nature of fractions, right? The denominator is smaller. That's going to give you a larger number. So we're not erring on the side of calculating a smaller s. We're being conservative, and it's safer. And somebody cannot then point to your calculations and say, hey, you calculated a quantity that works in your favor, and that's not good science, which would be a correct response. Again, it's because having n-1 in the denominator gives you a resulting number that is larger than having n in the denominator, and that's more conservative because smaller numbers are better. So if we report a slightly larger number, we can say, well, this is a reasonable number for the standard deviation, rather than we're going to assume the best possible situation or story around calculating the standard deviation. All right, now I'm going to move on, having answered that question, to this second measure of variability, which is range. It's a lot easier to calculate than the standard deviation. It doesn't suffer from a lot of issues that the standard deviation does, but you don't use it in, there's really not much in the way of formulas that you use the range for, but it can be used for that. Simply put, at its easiest, the range is the largest data value minus the smallest data value. So if your largest data value is 16 and your smallest data value is 2, 16 minus 2 is 14, that's the range. Okay, but more useful than that is the interval notation approach, which uses square brackets to express the largest and the smallest data points. So that's square bracket 16 comma 2 closing the square bracket, or just 16 comma 2. And when you use square brackets, it means inclusive of the numbers. So 16 including the number 16 to 2 is the range of the data including the number 2. And so this not only tells you the smallest and largest values of the data, it also allows you to say, well, 16 minus 2 is 14, and that's the range. You could also write this, no problem, 2 comma 16. Means the same thing. The range is still 14. Now, just to make it more complicated, because statisticians don't know when to leave a good thing alone, sometimes you use exclusive notation instead of inclusive notation. I tend to use only inclusive notation because it's easier to understand. But if you see a range expressed with parentheses, then it is excluding these two values. Now, assuming we're using integers, that this is like points on a test or something with no fractions, then the next highest number would be 17, and the next lowest number from 2 would be 1. And the parentheses indicate exclusive. So the range is excluding 17 to excluding 1, which would be, again, it's the same as 16 comma 2 using the inclusive notation. Just to make it more complicated, it's valid but not widely used to do mixed notation. So you could use an inclusive square bracket and an exclusive paren, and you could say 16 comma 1, and it would be including the number 16, but it would be excluding the number 1. So this implies 2 in the set of integers, so that you would still get a range. Your range, if you calculate it, was 14. This is not used very much, but I just thought I'd mention it in passing. That's about it for now. Thanks for listening. I'll see you guys in the next video. Have fun. Bye-bye.